So I think we can start our session. So yeah, before starting the session for today, Mr. Sitaram, do you want to say something? Yes. Okay. Okay. So yeah. So Sitaram, happy to have you here for this week 5 live interaction session. So let me just present my screen. So I hope my presentation is visible. Yeah. So yeah, let's start our session for today. So yeah, let me introduce myself. So good evening everyone. Welcome to the week 5 live interaction session for the course Waste to Energy Conversion. This course is offered by Professor Prasanajit Mondal from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati, is responsible for conducting the live interaction session every week. So we have almost finished half of the course. So today we are entering, week 5 uh, session is about to end by today. So till now we have learnt about how to convert waste to energy. So we have seen three preliminary routes from the very starting of the class. If you remember, the very first live interaction session or week one content was something that was dedicated to uh, having the basics of what are the different kind of what are the different kinds of process for converting the waste to energy. So there are totally three processes which we discuss. One was your thermal, another one is the chemical, as well as the third one was your biological conversion route. So in the thermal conversion route, we discussed again about three different types of conversion. One was incineration, second one was gasification, and third one was pyrolysis. We also discuss what how each process is different from each other and what is the basis of classification for each process, after which we discussed about uh, every particular conversion route in detail. So we discussed about gasification, the syngas production, the syngas utilization, and towards our week 4 live interaction session, we talked about densification method, and we started on understanding or basically calculating the efficiency, the thermal efficiency of the power plant. So the entire process of conversion, how to calculate the thermal efficiency, all those factors we discussed. So in today's live interaction session, we will be continuing on the efficiency topics. Like we, in the first module of efficiency improvement in the power plants, we discussed only about the useful energy, about how to calculate the heat rate and the efficiency. So as such, for every process we know in engineering as well as in every other processes that we do, always we do not attain 100% efficiency. The efficiency always remain lesser than 100 percentage. So we need to account or we need to understand why that efficiency always remains less than 100. So if the efficiency is not going to be 100%, then what about that extra percentage of the energy? Where is it going? What is the fate of that energy? Needs to be understood so that we can redesign the system in such a way that we can improve the efficiency percentage, no matter how large or small the increment in the efficiency is. Because from the industrial perspective, as I said in the previous session also, even a 1% increase in the efficiency of a process will lead to uh, decreasing the cost of the entire process to a larger extent. So that's how crucial is, or to be more specific, that is how much important is to you know work on the designing of the system so that the efficiency can be improved. So today we start with the with understanding of these different types of losses that happens within the system. So how many of you remember what is the expression, or how do you define the thermal efficiency of a power plant, or as such as how do you define thermal efficiency? Okay, Mr. Sitaram, you told that you have a small doubt, I guess. Yes, can you shoot it out? Excuse me, like, can you repeat your question? I am not actually sure about that particular aspect. So I would suggest you that if you have this, for you to post this question in the Q&A forum of Discord. So there you will be able to get the appropriate answer for this question, because I am not very well aware of this marking stuff. Yeah, yeah, that's what. I'm not exactly aware of that. Okay. So, I was asking about the different type of losses, or sorry, how do you define the thermal efficiency of a power plant, or what is the expression for the thermal efficiency? Yes. Yeah. So basically, as such, if you see efficiency, it is something like output by input. So here, since we deal with the thermal efficiency, we talk about the work as well as that of the heat input. So yeah, that's correct. So if you want to elaborate this expression, then it can be written as, just a second. Yeah, energy generation rate times T. So this is how it is defined in the course module. So I'm going to follow it exactly the same. Energy generation times T by mass times C, that is your heat capacity, specific heat capacity, the entire times 100. So this is about the thermal efficiency, and if you talk about the overall efficiency of the process, then you have to incorporate the efficiency of every single component in the system. That is your boiler efficiency, turbine efficiency, generator efficiency, work efficiency, and all the stuff. So here is what comes. So since the entire process of the power plant has multiple steps, so each step will incur some sort of losses. So let us list down all the losses, because they form a major portion of the module 2, relating to the efficiency of the power plant. So different type of losses. Yes, you are unable to like see my screen. Okay, just, yeah, yeah. You can see that losses in the thermal power plant, right? That heading. Yes, after that I've written the n. Yeah. PDF. Well, that is fine, but I won't be able to write. That is what I'm thinking. Hmm. Or let me do one thing. Let me stop sharing and let me try once. That will be fine. Is it okay right now? Okay, so that's fine. Again, as I said, here it is, the weather is not so good, so probably might be some internet issues might be there. So yeah, losses in the thermal power plant. So can anyone list what kind of losses in thermal power plants? I mean, what kind of losses do you expect while calculating the efficiency as such in a power plant? So one is due to the loss due to moisture. Yeah, so as such, when I said in a thermal power plant, I'm specifically focusing on the heat losses only. Something that is not used for the steam generation purpose. So the second one is the loss due to the heat loss due to unburnt carbon. So it is not, sometimes what happens is some amount of the carbon materials will not be totally burnt, so there might be some remaining carbon within the system, so that will also need to be incorporated while understanding the losses in the system. Then you will be having then if hydrogen atom is going to be present, or if hydrogen atom is going to be present in your feedstock, then what happens is chances of the hydrogen reacting with the water to form H2O will be more. So that is also like kind of taken as a moisture within the system, which will create a loss in the energy. Then loss due to dry exhaust gas. Another one is the loss due to incomplete combustion. So what happens is, if enough oxygen is not supplied, so carbon will not get converted to carbon dioxide, but rather to carbon monoxide. So that is an incomplete combustion process, because of which there might be some losses happening within the system. And the another most common loss that happens is the energy loss due to convection and radiation. After that, due to the presence of the formation of slag or ash, so they will try to take up the amount of heat. So this is a common problem within the boilers, not just in an industrial boiler, but even in case of the home also, this becomes a major issue. The slag, or kind of a thick layer that forms on the bottom of these kind of boilers, will prevent the heating efficiency, so the system will not be able to heat up properly because of this formation of the slag. They basically act like an insulator and heat insulator, and try to decrease the efficiency of the process. So due to that also, there will be some sort of an energy loss, because to attain that temperature what is required in the boiler, you tend to heat it more. So because of that, you try to use more raw material or more fuel. Because of that, the cost gets increased. So energy loss due to slag and ash formation or accumulation, you can say. So these are some of the losses that you can actually expect when you discuss about the losses in the thermal power plant. So every particular loss has a expression, so we do define it mathematically using equations. So I would suggest, as such, those who are present here as well as who will be watching it, to go through the course lectures, so that you will be able to find out all the different equations on how to calculate the loss in each different steps. So here we end with the thermal efficiency, or the efficiency improvement in the in the thermal power plant. After this, we move towards energy production from polymer, or you can say plastic waste. So plastics as such, if you see, are nothing but in the material field we call it as polymers. So polymers are the long chain of organic molecules. So they basically consist, so they are the repeating monomeric units which are connected to each other, forming a long chains. So these polymers are also used, the waste plastics that you throw away every day, starting from the plastic bottles that you use to the plastic covers that we use. So nowadays the usage of the plastic has been decreased, is reduced to a lot extent, but however we are unable to, what you can say, completely cut off or completely ban the usage of plastics. It still remains in some form of the other, in some form or the other it does, we do use them in everyday life. So these plastics needs to be used, and it can be converted to produce something so called as liquid fuel. So by doing this conversion of the plastic waste to fuel, we have two advantages, as we discussed this in the very beginning of our week 1 live interaction session also. So there are two goals by doing this waste to energy conversion. So one case, by converting the plastic to fuels, or by converting the waste to fuels, you tend to produce some energy materials which can be used for multiple other purpose. Apart from that, you also reduce or minimize the amount of waste that gets generated or accumulated within the ecosystem. So it's more so this uh, conversion of energy from waste makes the ecosystem more sustainable as such in a whole. So multiple different polymers are there. So there are a lot of different polymers that we use, starting from, I hope if you guys can give me some example of a polymer that you use in everyday life, it would be good. The most common polymer that we use every day. PVC. So PVC will be mostly in the form of pipes. Then your plastic bottles, if you have at home or if you are using it, they are made up of PET bottles. I hope you would have heard. And we use polythenes. So there are two different type of polythenes. So LDP, that is your low density polyethylene, and high density polyethylene. Like that, this polymers keep uh, you know coming, and we tend to use these polymers in everyday life as such. That's what I said, we have minimized the use of plastics, but we cannot completely ban the use of plastics. So one of the reason why it is important, I mean, why this plastic is basically interfering or is something that is considered harmful, is because these plastic wastes are not going to be biodegradable. They are not unlike your the other systems or other materials which gets degraded over a period of time. Like the biomass, they get degraded, they get decomposed and degraded and absorbed back to the soil if you leave it for some days. However, in case of the plastic, that lifespan for the degradation ranges from 100 to 1000 years depending upon the type of plastic. So they are not going to be easily biodegradable, they will remain within the ecosystem. So what happens is, if you throw majority of the plastic, if they find ways, in case through the oceans, what happens is the ocean gets polluted, and the land and the ecosystem also gets polluted. So what is a issue that is arising now. So I hope majority of you will be following the news every day. Nanoplastics and microplastic contamination in food, water, as well as there are also several reports where they found the the traces of microplastic present in the human body also in different organs. So this is what is one of the major issue that is coming up, and why plastic or why it is important for us to synthesize plastic or basically produce plastics which not only suit our needs but are also biodegradable in nature. Of course, there's a lot of research going on, so this is just a thing that I wanted to say. But coming back to the course, so these polymers are specifically used for the oil production. That is the main objective of converting the plastic waste. So again, depending upon the type of plastics, you will get different types of fuel, and there are certain plastics which may or may not be useful for our fuel production. So in case if your plastic, let's say it consists of compounds other than carbon and hydrogen, then it may not be suitable for the liquid fuel production. So majorly, as I said right now, since the plastics are not going to be biodegradable, you cannot actually expect to use some sort of a chemical conversion or a biological conversion method for converting this plastic to fuel production. So in this case, we typically go for the thermal conversion routes. So we take the plastic, we heat them up, and then from there we tend to what do you say, derive the liquid fuel. So out of the three processes that we use, as I said, as I discussed before, gasification, pyrolysis, and combustion, since we are producing a liquid fuel, pyrolysis is the best process. So uh, as such, before I ask, what is the difference between incineration, gasification, and pyrolysis? Anyone? Difference between pyrolysis, gasification, and incineration? Yes. Yeah. Okay. Gasification. So I would just like to make a small, sort of a correction here. When you say pyrolysis, it is better not to say absence of oxygen, rather than to, it is better to say in a very limited supply of oxygen, because you're tending to heat or burn a material, and oxygen is important for burning. So it is, but it is always right to say in the limited supply of oxygen, because even if you see in the course, we have said that the oxygen to the fuel ratio should be less than 0.68. So we did not say no oxygen is required. So this often remains as a this thing where people say absence, but I think it is better to say in a limited supply of oxygen. Again, as such, it's fine. So yeah, so there are two types of pyrolysis process which we can use it here in the production of fuel from the plastic waste. So one is the normal thermal pyrolysis and another one is the catalytic pyrolysis. So this we have discussed even in the pyrolysis section also, where we discussed about uh, you know what how catalytic pyrolysis is more beneficial compared to the normal pyrolysis technique. So can again, as I like to ask, can anyone tell me how is catalytic pyrolysis more useful compared to the normal thermal pyrolysis that we do, or that is utilized? Yes. Hmm. Hmm. Yeah, yeah, yeah. Yeah. Hmm. 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 So let me just write it down. First one is temperature reduction. Second one is residence time, or the amount, or to be in a layman sense, the amount of time that is required for the conversion of waste to fuel. Then I think the yield. Then apart from that, any, yeah. So the quality gets improved. So the fuel quality that you obtain, the liquid fuel quality, that will be improved if you use this catalytic process. Yes, all are right. So what happens is, if you use the catalytic temperature, if you use, sorry, catalytic pyrolysis process, you are actually going to use a catalyst. So that will tend to decrease the temperature. So instead of, this process happening at a temperature of around, let's say, 1000 or 1200 or 400 degrees Celsius, by using the catalyst you can reduce the temperature to 800 or 900 degrees Celsius. So the catalyst will help in temperature reduction. Again, how this process is beneficial, because if you reduce the temperature, since in order to reach that amount of temperature you require a lot of you know input fuel for the process. So if you use a catalyst, you can significantly reduce the amount of fuel that you're going to invest in this conversion process. Residence time will be lowered, yield will be good. So that is far better, because the product is going to be of better quality, as well as better quality, as well as the amount of product that you're going to obtain at the end will also be more. So this pyrolysis process as such depends upon quite a few parameters. So do we have any space here? A second. So pyrolysis process depends upon multiple factors, or you can say this catalytic pyrolysis process depends upon multiple factors. So again, let us instead of me saying I hope I wish to get responses from you guys. So what all you know parameters do you think can affect this pyrolysis process? Again, this is like an exercise, because when you talk about a particular process in you know when you talk about a particular process, we should be having a knowledge on what kind of parameters that could affect the process, or we should have we should try to develop this understanding on what could be the parameters that can affect this particular process. So this will help in designing of any systems. Yeah, plastic type. And then, yes, reactor type, whether is it going to be fixed bed or fluidized bed, or what is there's another one, the screw type reactor. Yeah, packed bed. Then after that, Again, you can also think of from with respect to catalytic pyrolysis process also. Yeah, type of catalyst. So amount of catalyst, how much catalyst should be added. Then you can say, if you talk, I mean, if you think from the normal pyrolysis process perspective, you can talk about temperature of the process, residence time. So yeah, we have almost covered all the process parameters. So these are the process which can affect your pyrolysis process. Types of feedstock. So whether you know the feedstock that you're going to use for your process is plastic, or if plastic, then what kind of plastic? If it is a biomass, what kind of biomass? What are the constituents of the biomass? Yes, yes. Hmm. Yeah. So one is yeah. So this I'll mention it here. That's a nice point to say. So thermoplastic and thermosetting plastic. So if it in case if it's a biomass, what kind of biomass it is, or what are the constituents of the biomass? Then coming to the reactors, what kind of reactor systems it is, whether as somebody said, fluidized bed, packed bed, or some screw type, or some other type of configuration. Yes. So in case of a fixed bed reactor, what happens is you will be passing the, let's say for example, I would, let this be an introduction session among the people in the audience itself. So can anybody tell what is a fixed bed reactor is? Instead of me explaining, I want the audience to say what's a fixed bed reactor. I mean, that are the advantages, but what is exactly fixed bed? I mean, hmm. So yeah. So fixed bed reactor, yeah, yeah, yeah. So fixed bed reactor is nothing but in case, in that case, what happens is the bed that you're going to use for the process is going to be fixed. Because if you see in case of the fluidized bed reactor, that bed as such where that combustion process or incineration process is going to happen, that fuel particle itself will be in motion. But here in our case, that particular what do you say? Yeah, you can say that fuel is going to be in the form of a fixed bed, so that bed is not going to actually move. Then we have types of catalyst, amount of catalyst, temperature, as well as residence time. So after this we will be going with gas cleanup. So again, we have something related to this polymer conversion process itself, but that is more of a self-read topics, because it basically involves a lot of case studies and stuff. So let me move on to something so called as gas cleanup. So if I'm not sure how many of you have attended the last session, or how many of you have seen the video of the last session, but there also we described about what is the need for this gas to be cleaned up. Why can't I just, like, whatever that gas that gets generated within the system, why can't I just leave it to the atmosphere? Yes. So homogeneous catalyst means that the composition of the system, that is, mm, how can I say? Example, I'm not very sure right now. Uh, again, mm, I need to look after what is the difference between, I mean, what is the example of that homogeneous cat. I would suggest you can look at the, yes, and so what do you mean by homogeneous means that the composition of the entire catalyst should be uniform, right? Hmm. In the composition, yeah. So again, example, I am not really very sure what are the examples. So if you are, interested in knowing the example, I would suggest you to look after the course. So yeah, yeah, yeah. Mm, yeah. Yeah, yeah, I did see. Instead of AlCl3, I think it is given as ACl3, right? Yeah, yeah, yeah. So I also saw that query. So, I hope the other TAs actually, there are also other people who are working in the background for this course. So I hope they will be able to respond to your question, sooner or later by this week. Yeah. Mm. Oh, perovskites. Uh, hmm. Perovskites, as far as if you talk about its structure, then from the structure perspective, it should be, if as far as my knowledge is concerned, it should be heterogeneous. Mm. So perovskites, one of the best example for perovskites is BaTiO3, barium titanium trioxide. So that structure, as such, it's not uniform throughout its the system. So it should be a heterogeneous catalyst. Mm. Okay. Okay, okay, okay. So, I mean, is this example given in the course lectures, or is it something out of that? Okay, 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 okay. Hmm. Hmm. FeCl3. Hmm. Hmm. Yeah, that's what. It is better. Actually, I would advise that it is better to wait for some time uh, because I'm not sure what the question is exactly, so I have to look after that question also. And this question, it is better if the people who are working for this, who are assigned for this assignment, actually respond to this. Hmm. Yeah, yeah, yeah. Okay, okay. Yeah, sure, 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 sure. Hmm. Hmm. No, 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 no. It will be answered. Yeah. Mm. Okay, okay, yeah, sure. Mm. Okay, I will just note it down and look after that. So week three, can you just tell me which question, if it is possible? Uh, hmm. Okay, yeah, sure. I will look after that, and then I hope this issue gets, what do you say, rectified as soon as possible. Okay, okay, okay. Okay, okay. I apologize for the mistakes that were done. So, yeah, yeah, yeah. Just like that. Why, I mean, why there is a need for the gas cleanup? Yeah. Hmm. So to make sure that the pollutants is less. So last time also we discussed that the particulate matters in the outlet gas should be reduced or should be less. So there is a board which is called as CPCB. I hope majority of you who might be attending may know. So Central Pollution Control Board. So they have some norms. So they have particular rules and regulations. Central Pollution Control Board. So they have some norms wherein you have to remove certain amount of the gases before you let out these gases in the atmosphere. So for this purpose, you actually require an entire setup, an entire system, so that that flue gas is removed and then is cleaned up before it is sent to the atmosphere, before it is sent to the environment. So for this process, we basically use multiple different type of equipments. So one thing what we have is for particulate matter removal alone. You have gravity settler, wherein you use gravity as the major source of what do you say, as a major source of force for to make sure that the particles get settled down at the bottom. So this gravity settler, one of the major, you can say, a disadvantage is that it cannot separate fine particles. The particle size should be greater than 50 micrometers. However, this gravity settler is a good what do you say, setup for pre-cleaning step. Yes, you mean power generation, steam turbine and gas turbine. So gravity settler is pre-cleaning step for particulate removal, and again, it is one of the most simplest method that you can use. So apart from that, you have something called ESP. So ESP full form is electrostatic precipitator. Third one you have is the cyclones. So where you use, so the major working principle of this cyclone is that you use the centrifugal force, and by the means of the centrifugal force you tend to make the particle or make the particulate matter settle down at the bottom of the setup, and through which you can remove it from the system. After that you have something so called as fabric filter. So these are for particulate removals, particulate matter removals. Apart from that, you have other gases for which you do some sort of scrubbing, dry scrubbing, wet scrubbing, and then you also do some other sort of the adsorption based process. So coming to this gravity settler, it is more often with the concept of gravity, where you use the movement of the particulate matter in the gas, and then you model the system. So you consider the gravitational force, buoyancy force, and drag force, and by balancing this force equation, you get the expression for the terminal velocity. So the next one is electrostatic precipitators. So let me put it in a presentation mode. Yeah. So here we will discuss about parallel plate type electrostatic precipitators. So the concept is, so here is a more three-dimensional, I mean both are three-dimensional, but here it is a more complicated diagram. But if you see the right hand side bottom, so an electrostatic precipitator, especially the parallel plate, consists of two plates, and in between the spaces between the two plates you have an electrode. So this electrode is connected to the negative terminal, and then the and then the collector plates. So this is the discharge electrode. Yeah, I hope it is visible. So my pointer is visible. So this is the discharge electrode, the one that you have at the center, and then the one that is present at the either side of the discharge electrode is your collection plate. So you can connect this discharge electrode to the negative terminal. So when the incoming gas with particulate matter enters in a direction perpendicular to these plates, what happens is, due to the high voltage in the discharge electrode, the gas matter gets ionized. So the particulates that is present in this gas gets negatively charged, so it acquires the charge of the discharging electrode. So because of that, since they have a negative charge and then your collector plates are going to be positively charged, they tend to move away from the gas stream. So from the main gas stream which is going in this perpendicular direction, the particulate matter that have a negatively charged particle is going to divert from this direction of motion, and then is going to get stuck onto the uh, collector plates. So that's what is written. The flue gas is going to be ionized, and the particulate matter gets negatively charged. The negatively charged particle are attracted to the positive collector plates or collection plates and get stuck there. So once a sufficient amount of the particulate matter gets stuck there, what happens is uh, a layer is formed on the surface of the collection plate. Once it reaches a certain threshold, these collection plates are disconnected from the setup, and then they are removed, and then they are just scraped off. So here, what is one of the parameter that you would like to see is the gas velocity between the plates is important. So why it is important is because what happens is, the gas velocity should be sufficient enough, so that what happens is that particulate matter that moves away from the discharger plate. So when they are going to be attracted by the positive collector plates, so that movement should not be affected. The particulate matter should not return back to the gas stream. So to prevent that from happening, we do this. To prevent that from happening, this gas velocity should be adjusted. So this is about ESP. Again, it's a very simple concept, but it is one of the most efficient one which is used in majority of the industrial process also. But again, it's a very simple concept where they try to use the electrostatic force as a basic principle for separating the particulate matter from your gas. So, with this, I think we have come to 1 hour session. So we would go towards solving some problems. So that is the main focus of this session. So in case if you have any doubts, you're welcome to ask me right now. I will address that question, uh, what do you say, later. So, because electrostatic at the table, because we need to know which kind of polymer is used for what. So, yeah, disposable food cups, plastic food boxes, plastic cutleries, and packing foams comes under polystyrene. So, if you have this carpet fiber, clothing, rope, medicine jars, or beverage bottles, so they are basically PET. So, PET as in full form is polyethylene terephthalate. Then comes is your containers for milk, motor oil, shampoos and conditioner, soap bottle, detergent and bleachers comes under HDPE. So the major reason why I gave this is because since these kind of there are chances for this kind of question is coming up in the assignment as well as the final exam is also there. So it is good to remember one or two example of each kind. So that would be better. Like for example, polypropylene, you have lunch boxes, margarine containers, yogurt pots, syrup bottles, and in case of LDP, you have squeezable bottles and plastic grocery bags, and PVC, you have pipes and tiles. Pipes is the best example, so many of us will know. So yeah, these are some of the examples. Yes, the second one, CH3, CH2. CH3, single bond CH, double bond CH2. Is it okay? Again, we have one question for that, so yeah, let's come to that quite sometime. So the first question is polystyrene. Again, the second one, as somebody rightly said, it's a fixed bed reactor. So I'm just going to mark that as fixed bed. Again, if you so somebody was asking, I think, what is a fixed bed reactor or how it looks. So I think they will be able to understand this. Then yeah, somebody asked about this polymer, right? So let's fill up the table before we move to the next two questions, the previous two questions. So you have to fill in the table and comment about their usability for the liquid fuel production. So the first one, column A is for polymer and column B is going to be for monomer. So what will be the monomer for HDP, high density polyethylene? Yeah. So CH2 double bond CH, yeah, ethylene. Yeah. And what about the monomer for, so the monomer is CH2 double bond CHCl. So what should be the polymer? Polyvinyl chloride. And the third one, six. So this compound name is hexamethylene diamine, and this is adipic acid. So just a very basic question, why we call it as nylon 66? Like, yeah, so each of the monomers has six carbon in their structure. So the main that CH2, that number is 6, so that's the reason it is named as nylon 66. So there is something also called nylon 6. So yeah, PS is polystyrene. So monomer, and yeah, styrene. Yeah. 36H5. Yeah. Polypropylene. So somebody as such they said propylene. Yes. Can you come back? Single bond. Yeah, that is N is polypropylene's this thing. I'm asking for the monomer, propylene. Yeah, so this is the what do you say? The monomers formula. So that double bond actually when it what do you say, undergoes addition reaction with the another propylene monomer, so they will form a bond together. At that time it will be like as what you said, CH2 CH, that way. So the last one, ABS, the diene styrene. Acrylonitrile, butadiene, styrene. So yeah, yes. Yeah, it's actually a sort of a rubber actually. So it's a very, yes, 3D printing. So you can use PLA, polylactic acid, or you can use polyurethane also. Because as such, when you say 3D printing, so I mean, as such, 3D printer, there are multiple type of 3D printing systems are available. So, hmm. So, polylactic acid and polyurethane, they can be used for this 3D printing purpose. Specifically, that filament-based 3D printing purpose, both of them will be suitable because they can be blend in the form of fiber wires. So, yes, yes, mm. Yes. So, the basis of differentiation is based on their molecular weight, and the second one is based on their density. So, as such, the name suggests high density polyethylene is more denser, and low density polyethylene is less denser. And in case of their molecular weight, high density polyethylene has a relatively more molecular weight compared to the low density polyethylenes. So that is the reason if you see there is a change in the application process also. So if you see this high density polyethylene, you can see the type of material that they are used, and if you see this low density polyethylene, you can easily come to know they are all in the form of bags. But if you go for high density polyethylene, they are in the form of mostly this container. So the mechanical properties of the high density polyethylene is kind of more compared to this low density polyethylene also. So but basis of differentiation will be on their molecular weight and density. Is that okay? Yeah. Yeah, containers for milk, motor oil, shampoos, conditioners, soap bottles, detergent and bleaches. Yeah. And then let's come to this numerical. Yeah. So calculate the amount of this is a question which I was asking I was discussing previously also. How much will be the amount of energy that will be lost? So we were talking about energy losses. So this is a question something that is related to that. So you have to calculate the amount of energy lost due to the moisture in the feedstock sample. You are asked to calculate the consider the feedstock to be of 100 kg and the moisture content to be of 30 percentage, and then the Tg, that is the outlet temperature or the exhaust temperature is 130 degrees Celsius. So you are expected to calculate the amount of energy lost. I will give one more addition here in kilo, sorry, kilojoule per kg. I hope equation is known to everyone, or shall I write the equation? Let me write the equation. So let me assume this, let me take it as Q. Q loss due to the moisture is M, that is your moisture content, times 4.187, 100 minus TA. TA is the ambient temperature you can take, plus, if I'm not wrong, it is 225, to 2000, sorry, 2225. If this is the latency, double two. So this is correct, right? What I have written. Yeah, okay, that's nice. And then you have the specific heat of the steam as 2.09, and this will be Tg minus 100. Yeah, kilojoule per kg. TA is the ambient temperature. You can take it as, I think, 25 degrees Celsius would do. I hope the formula is clear to everyone and there is no any ambiguity related to that formula. Okay, I'm supposed to calculate, and then only I will be able to tell the answer. So okay, that's fine. So I hope others are also solving. So let me just solve this. 100 minus 25. Hmm. Hmm. Yeah. So if I would have asked the answer in kilojoules, then you can actually multiply that 30 percentage. You can take it as 30, like 30 by 100 times the feedstock weight as 100. So then in that case, it won't be zero point 0.3, it will be 30. But here the question is given in terms of kilojoule per kg. So we are keeping the moisture content as zero point 0.3, like 30 by 100. Okay, that's fine. Let me just check the 130 minus 100. So we have 2.09 times 30, 62.7. So so if you add all this, then 26 33.525. 790.05. Again, if I would have, if the question would have been framed it in such a way, what it is for, like in the absolute scale for kilojoules, then you need to just multiply this with 100. So that would be the answer. But since here the question is not asked, it is asked in kilojoule per kg. So the Q, that is the amount of energy lost, will be in terms of 790.05 kilojoule per kg. So there are no doubts. I guess with the formula is clear for everyone, and then calculations are also fine. So let me just wait for 1 or 2 minutes in case if anybody is unable to follow, then please let me know. So I think we can go. Okay. So the next question is, I wanted to preferably take this question. So a municipal solid waste based power plant is emitting 33,000 meter cube per hour flue gas. It is proposed to install an ESP for the gas cleanup before releasing it out in the atmosphere. The total area of the available for the collection electrode is 300 meter square. Drift velocity is 0.20 meter per second. Now we are supposed to calculate the efficiency. So, and then we are also asked that, considering the fact that we require an ESP, the collection efficiency will be greater than 97 percentage. So we want an ESP which has a collection efficiency more than 97 percentage. If we want that, then how much additional area is required to accommodate the space for the collection of the electrode? I think this is a straightforward question. So, oh, sorry, my network was lost. So were we there in this question, or did my connection went off somewhere before itself? So anyway, so after that we are focusing only on this question. So I'll repeat the question once again. So we have a municipal solid waste based power plant which is emitting the flue gas at a flow rate of 33,000 meter cube per hour. Now we are going to install an ESP for cleaning the process. So the total area available for this collection electrode is 300 meter square. Now based on this collection area available, and then the drift velocity as 0.20 meter per second, we are supposed to calculate the efficiency of the ESP that can be installed within this area. Now we are asking that if the efficiency is greater than 97 percentage, calculate the additional area required to accommodate the space for this collection electrode. How much is the efficiency coming around? Okay. So what will be the answer for the question number B then in that case? Simple. So option B will be that you can just conclude that stating that we wanted an ESP which should have a collection efficiency greater than 97 percentage, and since in the first case itself we are getting a 98 percentage efficient ESP, so our answer is no additional area is required to accommodate the space, since the efficiency of the ESP is already greater than 97 percentage, which is our requirement. So anyway, let me write this. So can anybody tell the expression for this? Is my expression right? Just take one. Yeah. So Q is the flow rate, that is 33,000 meter cube per hour. But since it is in hour and our drift velocity is in seconds, so let's just convert that. 1 hour has totally 3600 seconds, so that will be 330 by 36. So Vm is 0.20 times your area is 300. Your Q, that is going to be 9 point, yeah, 1. I'm giving 9.167. So 300 times point 0.2 will be 60 by 9.1 double 167, 6.545. Oh, just a second. I'll use my personal calculator. So it will be around 1 minus. So it should be around 0.9985. So if you multiply that with 100 for percentage calculation, then it should be around 99.85. So did I make a mistake anywhere? Because I heard somebody saying 98%. What does the answer? Okay. So since it is, yeah, so but you are getting the answer for efficiency as 99.85 percentage, right? So here E is already greater than 98, greater than 97. So no additional area is required. Is this fine, or is there any ambiguity with my calculation or any issues from your side? Hmm. Yeah. Yeah, yeah, just a second. So it is coming around 0.00143. So, I mean, I guess I have double checked. So the efficiency is 99.85 percentage, and again, so the second question was just meant to add up, to just for the just to check whether people whether it makes it confusing, so that's the reason. So since ESP is, or efficiency is, greater than 97 percentage, so no additional area is required for the collection electrodes. So before that, okay, just a second. Okay, let's do this question. So this is something very similar to what is there within the course, so it's just for a practice purpose I have taken. A Venturi scrubber. A Venturi scrubber is used to collect the particulate matter from a gas stream. The liquid flow rate from the scrubber is 45 gallon per minute per centimeter per thousand centimeter per thousand feet cube per minute of the gas, and the relative velocity of the gas to the liquid is 200 meter per second. The gas is air, so it is at STP, and it carries particle with the density 800 kg per meter cube. So determine the efficiency of the scrubber as a function of the particle diameter. Consider the viscosity of the gas as 1.85 times 10 power minus 5 kg per meter second, and the empirical factor for throat geometry and other parameters as 0.25. Okay. So here, since the diameter of the, what do you say, particle is not given, so you are supposed to express the efficiency of the scrubber. So it is written efficiency of the scrubber is a function of particle diameter, so that's fine. So how do you write the efficiency of the Venturi scrubber or efficiency of the scrubber, that expression as such? So it is eta. I'm going to represent it as efficiency here is equal to 1 minus, is there any involved? Let me keep this at the. So this is the efficiency equation, and this can be written as C times density of the particle. So that we have with us dp square. So this dp square you are supposed to express in terms of dp's, because we don't have particle diameter given to us. So let's keep in terms of dc times vr, the whole divided by 18 do. So do will be the droplet diameter. Let me make it more, times your mu g. Yeah. So mu g is the viscosity of the gas. So this droplet diameter can also be written using this equation, wherein so the equation is 16400 by VR plus 1.45 L whole power 1.5. So here VR I have already mentioned in terms of meter per second, so you can just take it as meter per second, and you don't need to convert anything here, so you can just take it as meter per second and directly substitute there. So let's find the droplet diameter do. Your L is the liquid flow rate, so that will be 45. So if you calculate this, it would be 164 by 2, 82. 301.86. So the value for this is 519.71, if I am not wrong. Yeah. So you have now for the DO, so then you need to substitute this. Do we have space? Okay. This will be equal to C is a constant, you can keep it. dp, you have to express the answer in terms of dp, so that will be remaining as such. Vr, it is 200. dp you have got as 519.71 times mu g. Mu g is 1.8 times 10 to the power minus 5. So once you get the value of psi, you just need to substitute in that expression. So efficiency will be, again, since it's a equation which is going to depend upon the diameter, so let me write this. K is nothing but the empirical factor for throat geometry and other parameters. So that will be 0.25 times L will be again 45 times your this psi value times, sorry, power zero point 0.5. So if you substitute this in terms of C and dp, you will get an expression. If you solve this, you in terms of C and dp, you will get an expression for psi, and if you substitute here, you will be getting this efficiency equation. So this is a very same model question. It's just that the values are kind of, what do you say, changed. So here there will be another 800. It's just for practice purpose, so I will be leaving it here. So the answer to this will either we will take up in the next class, or I will post it in the PPT when whatever I'm going to, upload. So before this we had actually I just wanted to finish one question which is there pending in our basket for so long. So if you have any queries, then you can ask me, or we can go to these two questions which is there for very long period of time. I wanted to solve it always, but unfortunately we are unable to do it. So if you have anything there, you can ask me, or you can take up this question. It's just very simple one, and I wanted to finish this off today. and it will be also a recap for what we have learned in the first week one session. At least people will be able to tell me the formula. How do you define HHV in terms of LHV plus latent heat of vaporization, number of moles of water produced to that of number of moles of fuel combusted. So it's a very simple one. So we have HHV as 17120. We need to find the lower heat value. So let me keep that as X, or let me write it as LHV plus latent heat of vaporization will be 2250 times number of moles of water produced is 1 kilomole by number of moles of fuel combusted is 16. So 16979.375 kilojoule per kg. So this is just a straightforward question on how to use a HHV as well as LHV and then the equation relating both. So it is just that this question was pending with us for a long time, and moreover it will be a kind of a recap to everyone. So that's the reason I took it today itself. So like this we have one more question. I guess with that we can conclude our session for today. We have, yeah, one more. This is also from the previous sessions only, previous, I guess, week 1 or week 2 lecture content. So, we are supposed to find the solid content in a zero point 0.1 liter liquid waste. To do this, we have formulated a procedure wherein the liquid waste is transferred to a dish which weighs 300 grams. So the dish weight is 300 grams. Total weight of the liquid waste as in the dish together is 600 grams. Sample is dried, and after drying the weight is found to be 433.5. Calculate the total solids and volatile solids present in the liquid waste. Considering the fact that at 105 degrees Celsius all the what do you say, the water that is present in that liquid waste will get evaporated. So we need to, based on that aspect, we need to calculate the total solid content and the volatile solid content in the solid. So can I say total solid content is, so since I said that liquid waste all are going to be evaporated, and then the volatile matters are also going to get evaporated. So the weight that is obtained after the drying will be the dry weight of the sample. So that will be the solid content. So in that case it would be very simple math, it like everyday mathematics. So 433.5, and initially it was weighing around 300. This entire divided by the volume of the liquid waste, that is zero point 0.1 liter, so 100 ml. This together entirely, since we are asked to calculate it in percentage, I'll multiply that with 100. Or the 100 is not necessary, it's just whether percentage or not a percentage. So, or you can remove this. So what it would be, total solid content will be 133.5 by 100. So that will be 1.335. So this will be the total solid content in the sample. The volatile solids will be, so I think this can be calculated. So, mm, so this question is there. This we can take up in the next class. So I guess, yeah, that's all we have for today. So any doubts with respect to what we have discussed till now? Yeah, yeah, sure. Mm. Yeah. I think I have made some mistake while calculating the total solids content, if I'm not wrong. No, that is fine. Yeah. That's what, yes, exactly. So this, yeah. And this one will be with the petri dish also. I mean, with the dish also that we are taking. So, hmm, not 600. It should be 433.5. Just a second. So 600 will be the mass plus, uh, 300 grams is the dish weight itself. So to do this, we have formulated a procedure wherein the liquid waste is transferred to a dish which weighs 300 grams. So after drying, the weight of the entire system is going to be the weight of the dish plus weight of the sample. So that will be 133.5. Is it okay? So this should be 300 minus 133.5. Hmm. Oh yeah, fine, makes sense. Yeah. Hmm. So this entire calculation again will change. Was I correct in the first place or? Hmm. 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 So that is what is the volatile solid content. Hmm. 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 Yeah. Hmm. Oh, okay. Hmm. So is this fine? Yeah. Hmm. By 100, so the 1.335. So yeah. So that's all for today. If anybody else, and if any of you have any doubts, you are welcome to ask me right now. Yeah, okay. So let me conclude for the session for today, I think. So yeah, in case if you have asked any queries which are not answered, so I will try to put them in the, I have noted them down, so I will try to incorporate them in the slides when I upload them. So the recording for this session will be available somewhere in the next week between Tuesday or Wednesday. So thank you everyone for joining, and I hope I will be able to, I hope you all guys will join next week, or that is on next class is on 29th February. So I thank Professor Prasanajit Mondal as well as the NPTEL team for providing me this opportunity to interact with you all this Sunday afternoon from 5 p.m. to 7 p.m. So yeah, thank you and bye. Oh, sorry, that means 1st March, 2nd March, 2nd March. Okay, yeah. Thank you. Yeah.